Hi, my name is Rami Nabati and I'm here to present CenterFusion, center-based radar and camera fusion for 3D object detection. The perception system in autonomous vehicles is responsible for detecting and tracking objects. Autonomous vehicles usually take advantage of a variety of sensors to increase accuracy and robustness. The process of merging the data from different sensing modalities to reduce uncertainty is called sensor fusion. Sensor fusion in autonomous vehicles usually involves sensors such as cameras, radars, and lidars. In this work, we focus on the problem of radar and camera sensor fusion for 3D object detection. This figure shows sample point clouds from radar and lidar sensors in red and gray, respectively. Radar point clouds are usually extremely sparse compared to lidar point clouds, but each point conveys more information about the object, such as the relative velocity of the object, something that cannot be directly obtained from lidar point clouds. We propose CenterFusion, a method for radar and camera fusion for 3D object detection. We first use a center-based object detection network to generate preliminary detections. A center-based detection network models each object as a single point, the center point of its bounding box. Specifically, a fully convolutional network is used to extract the image features. A regression layer is then used to estimate heat maps representing the objects, and other regression layers are used to estimate size, depth, dimension, and orientation for each object. This results in image-based 3D detections, which might not be very accurate as the image does not provide any depth information. To exploit the radar information, we associate the radar detections to the corresponding objects on the image. Here on the left, you can see the radar detections mapped to the image plane. To accurately associate these radar detections to the objects, we introduce a frustum-based association method. We first create a region of interest frustum around every preliminary detection obtained in the previous step. We consider each radar detection inside this frustum to be associated with that object. We use the parameter delta to adjust the size of the frustum in the longitudinal direction. The image on the left shows the bird's eye view of a sample frustum and the radar detections that are inside it. Since automotive radars usually do not provide an accurate height for each point, we additionally expand each radar point to a 3D pillar. This is done to reduce the effect of the point's height in determining whether it's inside the frustum or not. If any part of the resulting pillar is inside the frustum, that radar detection is considered to be associated with the corresponding object. The generated pillars are then mapped to the image and converted to heat maps. Out of all radar pillars, only those associated to the detected objects are kept, and all the others are discarded. If there are multiple pillars associated to the same object, only the closest one is kept. The heat maps are generated using the velocity and depth values from the radar detections and are constrained to an area inside the 2D bounding box of each object on the image. This process is illustrated for the depth heat map in these images. The generated heat maps are then used as radar features to complement the image-based features. These feature maps are concatenated and fed into the secondary regression layers, which recalculate the depth and rotation values and also estimate the velocity and certain attributes for each detected object. The overall network architecture is shown here, demonstrating the flow of information from the image and radar point clouds to the final detection results. We use the nuisance dataset to evaluate our network. We compare our method with 4 others, including image and lidar-based methods. CenterFusion outperforms all other methods in the NDS metric, which is a weighted sum of the mean average precision and 5 other error metrics defined in the nuisance benchmark. Also notice that because of the utilization of radar velocity values in our network, CenterFusion obtains a significantly lower velocity estimation error compared to all the other methods. Here, the 3D detections are shown in both camera and bird's eye views. Notice that CenterFusion is accurately predicting the velocity of the objects, shown by the blue arrows in the bird's eye view plots. The red arrows represent the ground truth velocity. For more information, please check out our paper and source code, both available on the CenterFusion project page. Thanks for watching.